Okay, today we're going to use proof by induction to prove that a given expression is divisible by a certain integer. So we're going to prove some divisibility results. So I'll go through this in the first example for you. So for this one, we want to prove by induction that for all positive integers n, 3 to the power of 2n plus 11 is divisible by 4. And we're going to do this using the same method as we did for the other proof by induction. I'll rule a line before my answer. So my first step is to say, well, this function of n, let's say what I'm looking at is 3 to the power of 2n plus 11. And n is a positive integer. So the basis step, or the first step, would say, well, what happens when n equals 1? So f of 1 will be 3 to the power of 2 times 1 plus 11, which is 3 squared is 9 plus 11, which equals 20. Now, clearly, we know that 20 is equal to 4 times 5. So clearly we know that this is divisible by 4. So we can say this function of n is divisible by 4 when n equals 1. So we're saying we're proving it's true when n equals 1. So the next step is the assumption step, isn't it? So I'm going to assume that this is true for n equals k. So that means that f of k, which equals 3 to the power of 2k plus 11, is divisible by 4. So we're assuming that that is definitely divisible by 4. And the next step was this inductive step. So I'm going to say, well, what would happen if I wanted to find it f of k plus 1? So that would simply be 3 to the power of 2 k plus 1 plus 11. And here, that would be the same as, that would be 3 to the power of 2k plus 2. Now, remember, that would be the same as that times that plus 11. 3 to the power of 2k plus, or times 3 squared. When you times, you add. 3 squared is simply 9. So we can say that's the same as 9 times 3 to the power of 2k plus 11. So what I'm now going to look at, and this is where it's a little bit different for these ones, is if I were to now say, well, what would happen if I did f of k plus 1 minus f of k? So if we take those away, if these are both multiples of 4, the difference between them will be a multiple of 4. So we could say, well, what happens if I find the difference between these two things? So what happens if I do 9 times 3 to the power of 2k plus 11, and I subtract 3 to the power of 2k plus 11? Well, 9 of these will just be 8 times 3 to the power of 2k. 11 minus 11 is nothing. And normally, you know that this is divisible by 4, because you know 8 is divisible by 4, but normally just to show it really, really clearly, we could write that as 4 times 2 times 3 to the power of 2k. And then it makes it really clear we've got this 4 as a factor here. It makes it really obvious that you've actually shown it. So if I know that, this. So f of k plus 1 equals f of k plus 4 times 2 times 3 to the 2k, that. So what we're saying, if I know that this is divisible by 4, and it's obvious that this is divisible by 4, if they're both divisible by 4, they're both multiples of 4, when I add them together, the answer is also going to be divisible by 4. So we can say what we found here is, therefore, Fn is divisible by 4 when n equals k plus 1. That's what we've just shown. So the final kind of conclusion step, we're going to say, well, if Fn is divisible by 4 when n equals k, then it has been shown that Fn is also divisible by 4 when n equals k plus 1. But as we know that Fn is divisible by 4 when n equals 1, Fn must be divisible by 4 for all n that are positive integers by mathematical induction. So we start at 1, we show that's divisible by 4, we've shown that if it's divisible by 4, if we add 1 to that k, if k was 1, the next one will be divisible by 4, and so on. Okay, for this question then, you're asked to prove by induction that for all positive integers n cubed minus 7n plus 9 is divisible by 3. So what I'd like you to do is copy this down, then pause the video and have a go yourself. And then when you think you've had a go, resume the video and just check that what you've done agrees with the final answer. Okay, so we're going to start by saying, let this function of n be n cubed minus 7n plus 9, where n is a positive integer. So we always start with the basic step of f1. So f1 would be 1 cubed minus 7 times 1 plus 9. So that's 1 minus 7 plus 9, which is 3. So that is clearly divisible by 3. So that is divisible by 3. So we can say Fn divisible by 3 when n equals 1. So we proved it for n equals 1. Let's then do the assumption step. So I'm going to assume that it's true for n equals k, so that f of k equals k cubed minus 7k plus 9 is divisible by 3. And then I'm going to say, well, what happens if I do f of k plus 1? So f of k plus 1 will be k plus 1 cubed minus 7 k plus 1 plus 9. So k plus 1 cubed gives me k cubed plus 3k squared plus 3k plus 1 minus 7k minus 7 plus 9. So that gives me k cubed plus 3k squared minus 4k plus 3. So my next step then was to say, well, what happens if I subtract these? So if I do f of k plus 1 and I take away f of k, I'm going to get k cubed plus 3k squared minus 4k plus 3, take away k cubed minus 7k plus 9. And if I do that, I end up with 3k squared plus 3k. 3 minus 9 is minus 6. So actually, it's now pretty obvious that that's going to be divisible by 3. If I just factorise it by 3, I don't need to factorise anymore. So I know that then f of k plus 1 must equal f of k plus 3 times k squared plus k minus 2. So if f of k is divisible by 3, and 3k squared plus k minus 2 is obviously divisible by 3, I can then say, therefore, fn is divisible by 3 when n equals k plus 1. And then the very final step of this is to put your conclusion in. Remember, this is really important. You do get marks for this. I know it's long-winded. So if fn is divisible by 3 when n equals k, then it has been shown that fn is also divisible by 3 when n equals k plus 1, as fn is divisible by 3 when n equals 1, fn is also divisible by 3 for all n which are contained in the positive integers by mathematical induction.